Dear students, today we will see another application of Bernoulli's principle, and that is Pitot tube. It is actually a cylindrical tube which is used to measure the velocity in a flow region. It actually measures the velocity at a point. In the flow region. The flow region may be having an open surface, or you can say the free surface, open to atmosphere, or it may be some conduit or a pipe. So this is a device which is used to measure the velocity at any point or at a point of a flow region which may have a free surface, like you are having some fluid flowing in which there is a plate in the lower region and above region is free to atmosphere, or that there may be some pipe in which you want to find the velocity at a particular point. This was invented by Henry Pitot in mid 18, and in its modern form it was modified by Henry Darcy. So from the day of its invention, different modifications have been done in Pitot tube as per the requirement, and the modern type of Pitot tubes were invented in 19th century. These are used to measure the air speed in aircrafts, water speed of motorboats. Similarly, these are used to find the air, water or liquid velocity in industries. So Pitot tubes are very useful tubes. You can say that in aeroplanes, Pitot tubes are used to find the velocity. These are used at the wings because these measure the drag force, the lift force, and they also give us the measure of the force which is required to lift a aeroplane. Similarly, in water boats, these are very much useful, and in many industries, Pitot tubes have uses. The main thing is that Pitot tube measures the local velocity. These does not measure the average velocity in the flow region, rather they measure the local velocity. Now Pitot tube may be the two types which you will study. Otherwise there may be many types of Pitot tubes, but one is basic Pitot tube. In basic Pitot tube, you just have a cylindrical Pitot tube, a cylindrical tube you may see in this example. This is some flow region in which above surface is free to atmosphere, and this is the lower bed. And in this you want to measure what is the velocity at a particular point in the flow region. Suppose you want to find the velocity at point 1. Then this is a Pitot tube, which is a cylindrical type of tube having a bent at 90 degree. Let it be some liquid flowing in this region. So first of all, I am talking about the shape. This is the shape of basic Pitot tube. It points towards the direction of flow, towards the flow direction. So this is the flow direction, so it faces it. Number 2, it has no outlet. You see, it is closed from here, or you can say that no fluid may come out through this portion of the Pitot tube. इसको हम कहते हैं कि there is no outlet in the Pitot tube. No outlet to allow flow to continue. It simply means there would be a point in this tube where the velocity of the fluid will come to 0. We consider a point 2 here in the same level, such that from 1 to 2 there is going one stream. Now some important points are, one is static pressure and another is a stagnation pressure. By static pressure we mean the pressure exerted by fluid on a body or point which is at rest relative to fluid. This is called the static pressure. Another is stagnation pressure. Stagnation is actually a point where the fluid velocity becomes 0. That is, it is the point where the fluid comes to rest. So stagnation pressure is the pressure at a point where fluid comes to rest. In our problem, 2 is stagnation point. Now you understand the logic. 2 is the point where the fluid velocity will be 0. And you know the Bernoulli's principle that when the speed is 0, the pressure will be increased, because we have to maintain the balance between all energies. The sum of all energies is constant, and if speed is becoming 0, then naturally the pressure will be increased, and this is the increment in the pressure which will push the fluid to flow in this tube. And what will happen? The level of the fluid will rise in this tube. So this is the rise of the fluid level. Suppose it rises up to this level. So I can say that the point 1 is height h1. Point 2 is also at height h2, which is naturally h1 is equal to h2. And this level of height in this tube is h. ये समझ आ गया कि ये लेवल क्यों उठता है. यहाँ पर वेलोसिटी 0 हुई, प्रेशर इंक्रीज हुआ, एंड प्रेशर विल पुश द फ्लूइड टू फ्लो इनसाइड द ट्यूब. तो ये जितना लेवल उठ जाता है, यहीं से प्रेशर का हमारा मेजरमेंट होता है. जो स्टैटिक प्रेशर होता है उसको हम हाइड्रोस्टैटिक प्रेशर भी कहते हैं. दिस इज ऑल्सो हाइड्रोस्टैटिक प्रेशर और हाइड्रोस्टैटिक pressure. Okay. Now what we do? We will consider a stream which is going from 1 to 2. Now it is a same type of fluid, so the fluid density will be rho, and at point 1 pressure will be P1, velocity will be V1. At point 2, pressure will be P2, velocity will be V2. Now we will use the Bernoulli's equation at point 1 and at point 2. Now what the Bernoulli's principle says, that along a streamline, the Bernoulli's statement will remain the same at each and every point. That is the balance of energy. So we will write Bernoulli's expression for 1 as well as for 2. At point 1, we get P1 upon rho g plus V1 square upon 2g plus H1 is equal to C. This is the constant. You see, we may write Bernoulli's equation in this sense, or like P1 plus half rho V1 square plus 2g rho H1 is equal to C. We may write in both way. At point 2, it will be P2 upon rho g plus V2 square upon 2g plus H1. I am writing H1 because H1 and H2 both are same. Now from the 2, we see what is V2. V2 is 0 because it is the velocity at stagnation point. So from 1 and 2, 1 is equal to 2 by Bernoulli's principle. So P1 upon rho g plus V1 square upon 2g is equal to P2 upon rho g. I have not written H1 and H1 because both will be cancelled out. This implies V1 square is equal to 2g P2 minus P1 upon rho g. Now what is this P2 minus P1? This is the difference of the two pressures, and this is known as the dynamic pressure. P2 minus P1 is equal to dynamic pressure, and it is measured in terms of the height, the rise in the level of fluid. You may see here, whatever is the density of this fluid, it is rho. So it is measured in this term, rho, gravitational force, and this height. This is the column in this tube. Column length is h. So I will write rho. This is the density in the density of the fluid in the column. Rho, then gravity, and then h. So I'll put it in 3. So 3 implies V1 square is equal to 2g rho gh upon rho g, or finally it is 2 rho h, or V1 is equal to square root of twice rho, twice gh. This is twice gh, twice gh. Twice gh, it is twice gh. H is the column in bend tube. H is column in bend tube. Now one more thing which I would like to tell you is that there is one velocity which is actual and another is which is theoretical. This is the theoretical value which we have found, and this is V actual. In actual, your fluid is viscous, but we have assumed the fluid to be ideal. So assuming the fluid to be ideal, that is non-viscous, we have found V theoretical. In actual, V is viscous. So what will happen? The velocity value theoretically found will be greater than the actual value of the velocity. And the ratio V actual upon V theoretical is called coefficient of velocity. This is called coefficient of velocity. So when you want to find V actual, this will be CV V theoretical. And the second thing is that the diameter of the Pitot tube should be greater than 10 mm. The reason being, if the diameter of the Pitot tube is less than 10 mm, it will give you the effect like the capillary tube. And so it will not give us the required information. So in order to avoid the capillary effects, the diameter of Pitot tube should be greater than 10 mm. This is the condition. So it is one type of Pitot tube, which is a very basic Pitot tube, very simple Pitot tube. Now you may have the situation when you are having a conduit or a pipe and you want to find velocity at some point of it. So in such cases, we have another type of Pitot tube to measure velocity at a point in a conduit oblique pipe. In such case, we, with the help of simple Pitot tube जो हमने अभी देखी थी, we can measure only the we can only measure the stagnation pressure, stagnation pressure. And to measure static pressure, one separate tube is used which is called piezometer. Piezometer. Second thing is that static pressure is measured near the wall. Of the boundary. Now it would be better that we first draw it and then you may understand it more clearly. Suppose this is a closed pipe. In this pipe, we want to measure the velocity at a point. So we will add a simple Pitot tube This is a simple Pitot tube. And this is the piezometer. And this is simply a basic Pitot tube. Then what we do, we connect the two tubes with the help of a, you may take this type of manometer. Oh, this is very poorly drawn. This is piezometer. And now both of these are connected. Still it is not in good position. Actually, I want to have one level high. मुझे थोड़ा गैप लेना पड़ेगा, एक्चुअली बन ही नहीं रहा है ये. जस्ट अ मिनट. बाप रे, तुम लोग भी सोच रहे होंगे क्या हो गया. Now it is okay. Though it is still very bad. So मुझे ये दिखाना था जिसकी वजह से इतना टाइम लग रहा था. Similarly, as in the previous article, this is point 1, this is point 2. Now you look at it. I have said that static pressure is measured near the wall. So this is near the wall of the boundary. Boundary is smooth. This is a condition, and this condition is taken, the boundaries are taken to be smooth because the streamlines near the surface will be straight lines, not the curves. Streamlines adjacent to the boundaries are not curved. Okay. Now the ends of Pitot tube, ends of Pitot tube and piezometer are connected to each other. This is the end of, this is the end of piezometer, and this is the end of Pitot tube. So both of these ends are connected by a manometer. And this manometer is containing some fluid. Suppose it is containing mercury. Containing mercury of density, कुछ मान लेते हैं इसकी density से sigma. Now you see, your stream is going from 1 point to 2 point, and 2 is the stagnation point. At this point velocity will be 0, and this velocity will be converted into the pressure, or it will increase the pressure, not converted, it will increase the pressure. Due to the increment in the pressure, the fluid level will rise in the tube, and this will go in upward direction, and the mercury in the manometer will be pushed by this fluid, and it will go high in its second part. Suppose its level go like this. Now you see, this is the column. This is the column. Okay. Now we will use the flow. We will use the Bernoulli's equation to calculate the flow velocity. Calculate velocity at point 1. So we will use now the equation like in the previous article. We will write Bernoulli's equation at the 2 point. At 1, P1 upon rho g plus V1 square upon 2g plus Z1 is equal to constant. Z1 or H1, whatever you want to take. P2, now at 2, P2 upon rho g plus V2 square upon 2g plus Z2 is equal to constant, and both of these will be same. Further, V2 will be 0, Z1 will be equal to Z2. So we are left with V1 square is equal to twice G upon rho P2 minus P1. Again, this P2 minus P1 will be measured with the help of this column. So it will be sigma, density of mercury, gravity force and height of the column. Putting in one, V1 square is equal to twice G sigma G तो यहाँ से कैंसिल हो जाता है, ये G नहीं है यहाँ पे, twice G sigma H upon rho. This is velocity. Square root of twice G sigma H upon rho. And it is the theoretical velocity. So as in the previous article, V actual will be coefficient of velocity into V theoretical. So it is the end of this application. Similarly, there are some other applications of Bernoulli's equation, which I'll tell you in next lecture.